Okay, today we're going to be going over the Maths Methods 2019 Short Answer Unit 2 exam. So to start off, we've got this problem here. We've got 3 to the power of 4x take away 1 is equal to 1/9. When we're solving these problems, we need to make sure that we have the same base on both sides of the equation. Then we can just set our powers equal. So at the moment, we have 3 to the power of 4x minus 1. I'm just going to leave that be. But my 1/9, I'm going to rewrite that. I'm going to rewrite that as 3 to the power of negative 2. The negative comes from the fact that I need to move it from the 9 from the denominator to the numerator, and the 2 comes from the fact that 3 squared is 2. Now I have my bases the same. I can set my powers equal, my exponents equal. So I can say 4x take away 1 is equal to negative 2. Now this just becomes a simple linear equation to solve. So 4x equals minus 1, x equals negative a quarter. In the next problem, we have some logarithms that we need to solve. So if we're going to solve a logarithm problem, we need to have a single log, and then we can do whatever the base of that log is to the power of both sides. So the first thing I need to do is I need to combine these 3 logs that I've got here together into one single log. Before I can do that though, I need to make sure that they all have the same coefficient of 1. So I'll leave this log base 2 of 2x, I'll leave that be now. I will shift this coefficient of 3, into my power inside the log. So this will become log base 2 of 4 cubed, and then plus log 2x squared, all going to equal 1. So then now we've got these, we can put these together. We have a log base 2 take away another log base 2, and they both have a coefficient of 1. So we can write these as division. So this can become log base 2 of 2x over 4 cubed, and then we have plus log base 2 of x squared, still equal to 1. And now, since we have 2 logs that are multiplying, we can combine the logs together by multiplying whatever's inside the logs. So we'll get log base 2 of 2x on 4 cubed times x squared. This will be equal to 1. So let's clean up what we've got in here, what we've got inside our logarithm a little bit. So this will be the same as log base 2 of 2x cubed on 64. 4 cubed is 64. So I'm going to simplify this down to x cubed on 32. And this is equal to 1. So now I've done this, I need to get rid of my logarithm because it's all together in this nice single log base 2. So to get rid of a log base 2, I do 2 to the power of both sides. When I do that, I end up with x cubed over 32 is going to be equal to 2 to the power of 1. 2 to the power of 1 is just 2. I'm going to shift over to here so I've got a bit more space. So I multiply both sides by 32. I get x cubed is 32. Sorry, it's 64. And so x has to be, whoops, not 8. X has to be 4. So when we were marking this problem, there was 1 mark for getting to this stage here, for combining the logs together, and then 1 mark for the answer for x equals 4. In my class, a few students got tricked by this x is greater than 0. This is just something that you need to have whenever you're dealing with a logarithm. You can't take the logarithm of 0 or the logarithm of a negative number. Logarithms are not. Okay, this next problem was one that was probably one of the most difficult for my class. So what we need to do in this one, we need to solve this function tan of root 3 times tan of 4x is equal to 1, for x is between 0 and pi on 2 non-inclusive. So whenever I have a problem like this, the very first thing I want to do is I want to get one side of my equation looking like tan of x or sine of x or cos of x, so that way I can take the tan inverse, the sine inverse, the cos inverse, whatever I need. So to do that, I need to get rid of this square root 3, which I do by dividing both sides by square root 3. So I'll get 10 of 4x is equal to 1 on square root 3. You could rationalize the denominator here, but if we do that, it's going to make it harder for us to use our equivalent triangles. So usually, we just charge on ahead and do tan inverse of both sides. But the fact that we have 4 times x here means that we need to be more considerate of our domain for this problem. You might have a different way of doing this. The way that I like to think about this is, rather than dealing with this tricky problem, I'm just going to say some variable a is equal to 4 times x. So to go from x to a, I multiply by 4. So this means that my domain is going to become whatever the domain of x is, but multiplied by 4. So a is going to be a subset of 4 times 0 through to 4 times pi on 2, non-inclusive. And this is equivalent to if we just go between, so this is the same as saying a is between 0 and 2 pi. Cool. So we're looking for solutions. If we're solving this tan of 4x with a instead of 4x, then we need to look between 0 and 2 pi. So let's do that now. We make our substitution. Tan of a is equal to 1 over the square root of 3. Now we've got this, we go to our special triangles. So I see this, I look at 1, I see square root of 3. I know this isn't going to be an isosceles triangle. So I draw up my triangle. I know my sides are square root 3, 2, and 1 by Pythagoras. And I know that the shorter side goes with the larger angle. So this will be pi on 3 here. This will be pi on 6 over here. So I'm now looking for tan. Tan is opposite over hypotenuse. So where do I have an opposite of 1 and tan is opposite over adjacent. Where do I have an opposite of 1 and an adjacent of square root 3? Well, it's got to be a pi on 6, doesn't it? So we can say a is equal to pi on 6. But this wasn't enough. We also need all the solutions from 0 to 2 pi, not inclusive of 2 pi. If I draw up my unit circle, my SATC, the pi on 6 solution, well, that's going to be here. This is my reference angle. It's going to be in the all quadrant. That's fine. We're looking for a positive tan, which means we'll also need to be looking in the tan quadrant. So we look around to our nearest x-axis, which is at pi, and we say, okay, we're going further along our unit circle, so it needs to be pi plus the reference angle. Pi plus pi over 6, which is the same as my solutions being at pi on 6, 7 pi on 6. But this might seem like we've solved the problem, but the thing is, we've only solved it for a. We need to solve it for x. So I can make my substitution back. I can make my substitution a is the same as 4x. So these numbers that I've got here, these are the same as a. So this is going to be equal to 4x. So this means that I divide both sides by 4. That will give me my x value. So pi over 24, 7 pi over 24 is equal to x. And if you're feeling a bit apprehensive about the domain restrictions, you could check, is pi on 24, is 7 pi on 24, are they between 0 and pi on 2? And yes, they are. Okay, for this next question, 3a, we need to find the derivative of x minus 1 times 3x plus 2. So if we're going to do this in Year 11 Math Methods, to find any derivative, you need to be in an expanded form first. So the first thing we need to do is expand this. So when we do that, we get 3x squared plus 2x minus 3x minus 2. And we could combine this, but I'm just going to differentiate it straight away. So we get 6x plus 2 minus 3, 6x minus 1. For the next part, part B, we've got this function g of x. We're told that x has to be greater than 0. We need to find g dash of 2. And we've got this specific form that it wants us to put our answer in. So first things first, let's find g dash of x. If I'm going to do this, whenever I have square roots, whenever I have variables on my denominator, I want to rewrite it with the variables on the top and with negative powers or fractional powers, whatever it need be. So g of x, I'm going to rewrite as x to the power of a half, because the square root is the same as to the power of a half, minus 3x to the power of negative 2. And so when I differentiate this, I'll get g dashed x is going to be equal to 1/2 times x to the power of negative 1/2 plus 6x to the power of minus 3. So this is my g dashed of x, but I need g dashed of 2. So g dashed of 2 just comes from substituting x equals 2 in. Actually, I'm going to rewrite my g dashed of x just to make it a little bit easier for me to work with before I do that. So this will be the same as 1 on 2 square root 2 plus 6 over x cubed. And then when I do this, so this should be x here, not 2. So now I combine g dashed of 2 by substituting x equals 2 into this, so I'll get 1 over 2 times the square root of 2 plus 6 over 2 cubed is 8. But I see this, I know that 6 over 8, well, that's just the same as 3 over 4. Cool. So this is what g dash of 2 is, but I need to express my answer in the form that they want. I need to express my answer as square root of a plus b over c. So when I look at this, first thing I notice, I've got two fractions, it wants one fraction. So I need to put these together. So what I'll do is I'll multiply this fraction on the left, I'll multiply that by 2. So I'll get 2 over 4 times the square root of 2. And this fraction on the right, I'm going to multiply this by square root of 2 over square root of 2. And so I'll get 3 times the square root of 2 over 4 times the square root of 2. Now I have a common denominator, I can put these two fractions together. So I get 2 plus 3 times the square root of 2 over 4 times the square root of 2. So this is looking good. We've got the one fraction, but you might notice that this c, it's a positive integer, so I can't have a square root on the bottom. So I'm going to move up to here. The way that we get square roots of the bottom is we do the technique of rationalizing the denominator, where we multiply by a fraction that has the numerator and the denominator both as whatever the irrational part of our denominator is. So in this case, the irrational part of the denominator is square root of 2. So we multiply by square root of 2 over square root of 2. And so this will give us 2 square root 2 plus 3 root 2 times root 2 gives us 3 times 2, which is 6, all divided by 4 times the square root of 2 times the square root of 2 is 8. And let's just clean it up a little bit. We'll get square root of 2 plus 6 over 8. Plus 3 over 4 for our final answer. So A is 2, B is 3, C is 4. Okay, for this next question, we have this function h dashed of x, which is equal to 1 on x squared minus 2 square root of x. And we're told that h of 1 is 0. We've got to find h of x. So this means we're going straight to integration. Just like before though, anytime I'm doing any differentiation or integration, I want to make sure that I have all of my values with powers shown on the numerator. So I'm going to turn this into h dashed of x equal to x to the power of minus 2 times x to the power of a half. And so then if this is my h dashed of x, then h of x is going to be equal to the integral of this. So the integral of x to the minus 2 minus 2x to the power of half dx. That's the indefinite integral. I don't have any terminals. So this will become negative 1 over x minus 2x to the power of 3 halves, all divided by 3 halves, plus some constant c. So let's just clean this up a little bit. The negative 1 on x is fine. This stuff here, I've got some stuff on the top being divided by a fraction. If I divide by a fraction, that's the same as multiplying by the reciprocal. So I end up with minus 4x to the power of 3 on 2, all divided by 3. And then plus c is still plus c. So I know with this that h of 1 equals 0. And so this is going to be the same as if I substitute 1 into my expression. So negative 1 on 1 minus 4/3. I'll write it out the front so I can be a bit neater. Times 1 to the power of 3 halves c. And so if I continue on from here, I can group the terms on my right hand side together. So I get minus 7/3 plus c is equal to 0. So c has to be 7/3. And so then altogether we end up with hx is equal to negative 1 on x minus 4/3 of x to the power of 3 on 2 plus 7/3. So the next part, we've got a nasty looking integral. If you tried to do this without simplifying the fraction first, you would have done it almost certainly incorrectly. This is very difficult to do without it, but luckily we can just rewrite this. So we have the same common fraction of x squared. So we have the same common denominator between our terms of x squared. So we can just divide each of our numerator terms by x squared to do this. So when we do this, we'll get x cubed divided by x squared gives us x, and then take away 2x squared divided by x squared gives us 2 dx. And so then we can carry out our integration. So x will become x squared over 2 minus 2x, and then this goes between 4 and 2. So now we can do our substitution. We'll get 4 squared is 16 over 2 minus 8. Take away, let's see, we've got 2 squared is 4. So 4 over 2 minus 2 times 2 is 4. So this first term, 16 over 2 is 8. So 8 take away 8 is 0. And then we're subtracting. We've got 4 over 2 is 2. Minus 4 gives us minus 2. So all up out of this crazy looking thing, we just end up with 2. Okay, for this next problem, we've been shown two graphs. F of x on the left is a parabola. G of x on the right is a logarithm. First thing we need to do is we need to state the range of x. So thinking back to semester 1 when we were talking about the different ways that we can represent quadratics, this is a quadratic in turning point form. The turning point form, since it's a minimum parabola, we know that the turning point is going to be the smallest value and it's going to be inclusive, and based off of the turning point form it's going to be from 1, and quadratics don't have an upper limit if it's a minimum, so it's going to be 1 through to infinity, not inclusive. The next part of this problem is asking us to sketch the graph of g inverse, which is the inverse function of g, on the same axes. We've got to label any axis intercept with the coordinates and any asymptotes with their equations. So anytime you're thinking of sketching an inverse, you want to draw a little dotted line. This line is y equals x. This is what you will use to try and sketch a line. So from here, you have two options. You could go ahead and just kind of do it by eyeballing, making sure that you get the same number of x-intercepts in the same place on the opposite axis, or you can do it by finding the actual specific inverse function itself. So I'm going to do it by finding the inverse function itself. So if I have y is equal to log base e of x, then the inverse function will be x is equal to log base e of y. So e to the power of x is equal to y. And in this case, e is being used as Euler's constant, which is not a variable, but it's a specific number. So now we know this. We know e is a positive number, so we can sketch. We know we're going to have a positive exponential graph. It's going to have an asymptote at y equals 0, and we're going to have a y-intercept at somewhere. We could have also got this by looking and saying, hey, the function I'm finding the inverse of that has a asymptote at x equals 0 and a 1 x-intercept. So my inverse function must have an asymptote at y equals 0 and 1 y-intercept. There it goes. So I need to label my axis intercepts with coordinates, and an asymptote with the equation. So I can label my asymptote with the equation real quick. There it is. Y equals 0. That's one part of it. To find the value of the x-intercept here, so the y-intercept here, I can set x equal to 0. So I get e to the power of 0 is equal to y. Anything to the power of 0 except for 0 is 1. So 1 is equal to y. So this coordinate here has to be at x equals 0, y equals 1. Right. This next question was a bit of a doozy. So at first glance, it looks like you need to show that this cubic function here is the same as this factorized cubic function here. So going from the polynomial form of a cubic to the factorizable form of a cubic is not something that is particularly easy. If you're going to do this, what you need to do typically is you need to long divide, you need to find a factor. In this case, it's pretty obvious that x equals positive 3 and x equals negative 1, they're going to be factors, but you would still need to substitute them in and verify that those values are 0, and that will tell you that it's a factor. And then you can do your long division. It's going to take you about 15 years to do, and there's so much room for mistakes along the way. For 1 mark, not really worth it. What you can do instead is, rather than trying to show that your left-hand side is the same as your right-hand side, you can show that your right-hand side is the same as your left-hand side for this. So if we're going to do that, all we need to do is expand the brackets. So I'm going to expand my x plus 1 first. So I'll just leave my x minus 3. I'll just leave that b for now. X minus 3 here. And x plus 1 squared becomes x squared plus 2x plus 1. And then if we keep expanding this out, we'll get x cubed plus 2x squared plus x minus 3x squared minus 6x minus 3. And then if we just clean this up a bit, we get, like it wanted us to get, x cubed minus x squared minus 5x minus 3. Perfect. Way easier, right? So that one, there's a nicer, easier way to do it. This next one is it's not so good. So we've got to find the coordinates of the stationary points of x. Well, this should probably read f of x rather than the stationary points of x. Anyway, we need to find the stationary point of this function f of x. Anytime you see this word stationary point, you go straight to the derivative and you find when that derivative is equal to 0. So f dashed of x is going to be 3x squared minus 2x minus 5. And we're looking for the stationary points. Stationary points when your gradient is 0. So we set f dash of x is equal to 0. And that's going to be equal to 3x squared minus 2x minus 5. We have here a quadratic. You can factorize this quadratic to solve it and use an null factor law. You can use a quadratic formula, whatever you want to do. I'm going to factorize it. When I factorize it, I will get 3x minus 5 equal to, times x plus 1. Cool. So this gives me x solutions of x of 5/3 and 1. This would be half of the marks for this question. We need to find the coordinates. Coordinates means you need an x and you need a y. So let's start with the 1, because that's probably a bit easier to deal with. I could substitute it. I'm going to substitute this back into f of x. I could substitute it into either form. I could substitute it into my factorized form, or I could substitute it into my expanded form. It's going to be easier when I do this. Because I've got this fraction, I've got this 5/3. If I'm cubing that, cubing 5/3 gives me so much room to make a mistake. But if I use the factorized form, then the highest power is squared. So that will be easier for me to deal with. So when I'm doing my substitution, I'm going to go into the factorized form. Factorized form is easier for doing substitution 99% of the time. So we'll say f of, we'll start with -1. This should have said -1 from the start. I do apologize. F of -1 is going to be equal to -1 minus 3 times -1 plus 1 all squared. -1 plus 1 is 0, so this immediately becomes 0. Whoops. Next, let's do so this overall coordinate is -1, 0. Next, let's do the other coordinate, so f of 5/3. When we do this, I'm going to use the factorized form again. so many students spent too much time on this exam substituting into the polynomial form, and they still made mistakes. It was very sad to see. But if we do it into the factorized form, it's so much better. Let's see. So we'll have 5/3 minus 3 times 5/3 plus 1, and then that's all squared. So if we do 5/3 minus 3, that ends up giving us 4/3, and it's negative. And then 5/3 plus 1 will give us, mental maths is telling me that it's 8/3, and then that's being squared. So then when we work this out, we'll get negative 4/3 times, let's do the square, so 64 over 9. 4 times 64 is going to be 256, so we'll get negative 256 over 27. Nice and simple, right? But it's way easier to do it like this than to have to cube 5/3 and then square 5/3 and then multiply it by 5 and then add on 3. So our overall coordinates are going to be 5/3 negative 256 over 27. So in this next part, we need to graph the function f of x. We need to make sure we label our axis-intercepts, our stationary points, and endpoint. So we found our stationary points in the last slide. We found that there was one at -1, 0, and one at 256, sorry, negative 256 over 27. So if we're going to do that one, we're going to need to work out where it is. So if we rewrite negative 256 over 27, hopefully you all know your 27 times tables. I know I do. So I know that it is the same as, I know it's the same as 9 and 13 27ths, which is more or less 9.5. So our stationary points, just to remind us, are at -1, 0, and 3, negative 9.5 or so. So let's put that second one in. Sorry, at 5 on 3, not at 3. So let's put the first one in. We've got the first one in there. We need to put the other one in at 5 over 3 and about negative 9.5. So that's probably here or so. You don't need to be exact with these. We know you're just doing it by hand. So that's our stationary points. Those are done. We need now our axis-intercepts. So this is the one time when I think that this polynomial form is more useful, when you're finding the y-intercepts. So to find the y-intercept, we just let x equal 0. So we're just going to end up with -3. Here it is here. And then we need our other x-intercept. Hey, my point disappeared. We need our other x-intercept. So you might remember our equation, our other form of f of x was x minus 1, so x plus 1 squared, x minus 3. So our other x-intercept is x equals 3. The last thing we need, so we've got our axis-intercepts, we've got our stationary points. We also need the endpoint. So the endpoint, we can't find the endpoint on the right-hand edge, on the larger edge, because that's infinity, too big, can't draw it. But the left-hand edge we can find. We know that this graph finishes at -2. So we need to find f of -2. We need to find the value of the function at -2, which is going to give us -2 cubed, or cubed, minus -2 squared, -5 times -2 minus 3. And you could also use the factorized form to do this. That would be completely valid, and it probably would mean that you would make less mistakes, potentially, depending on whether you feel more comfortable with cubing negative numbers or multiplying them. And so if we put all this together, we end up with -5. So our other point is going to be x equals -2, y equals -5. And we've got to make sure with this one, you've got to have a solid dot. It's got to be a solid dot because we are including x equals -2. Last thing is look at the shape of this. We know it's a cubic, so it's either going to be like this, or like this. We can straight away tell just by kind of putting the dots together that it's going to be this positive cubic. So like that, except going through the point 3. Again, the shape doesn't matter too much. Try and get it right. Try not to make mistakes. But the key things we're looking for here, getting the right overall shape and labeling the correct points. Let me just give that another go. There we go. Ah, I did it again. Oh well. So I'm going to label these because it specifically tells me to label. It's not good enough to just put the points on there. So 3, 0, 5/3, -9 and 13/27, 0, -3, -1 and 0, and then -2, -5. Awesome. Easy. We got it. Cool. So this one was a big question, and there was a lot of places for people to make mistakes, but there are a lot of marks on the line as well. You could get 5 marks for this for what is essentially the same kind of thing, not exactly, but the same kind of thing as the hurdle task that we did earlier in the year. So we're told that the kitchen bench top, it's got 2 rectangles cut out so that we can get sinks. The smallest sink is X, the widest sink X by Y, and the biggest sink is 2X plus 5 by 2Y. And we're told that the total length, so the total perimeter that we're cutting out is 310. And we need to find the length and width of the larger sink, so the big one, if the total area is to be a maximum. So straight away, you see this total area is to be a maximum. That tells you that 1, you're going to get an area function, and 2, you're going to take the derivative and find the stationary points, find the maximum. If we do this, well, I'm going to set up my equation for the area. So I know from the smaller rectangle, I'm going to have x times y, plus from the bigger rectangle, I'm going to have, well, we've got a width of, a length of 2x plus 5, and a width of 2y. So put these together, here it is. But hold on, we've got a problem. We've now got to differentiate something that's got x and y in it, and we can't do that. In Math Methods Unit 2, you do not differentiate things that have more than one variable. So we need to cut out one of these variables. Luckily, we know that the total length of all cutting required is 310. So that's a bit of extra information we can use. The total length of cutting, well, that's the same as the perimeter. So we can say 310 is going to be equal to 2x plus 2y. That's the perimeter of the smaller rectangle. Plus, and then for the bigger rectangle, we've got 4x plus 10 plus 4y. Those last two are the perimeter of the larger rectangle. So smaller is 2x plus 2y, larger is 4x plus 10 plus 4y. And so if we put this together, let's just combine this down. So we'll get 300 is equal to 6x plus 6y. So then let's get one of these in terms of, let's rearrange this in terms of y, because then we'll have something that looks like y equals. We can substitute that into our area expression, and we'll just get x by itself. We'll get a in terms of x. So if we do that, we'll get, we'll divide both sides by 6. We'll get 50 is equal to x plus y. So y is going to equal 50 subtract x. Cool. So we've got this now. So I'll rewrite it up here, and we'll substitute in x, y is equal to 50 minus x. So we'll get x times 50 minus x plus 2x plus 5 times 2 times bracket 50 minus x. So this is just my area equation, but with y is equal to 50 minus x substituted in. So if I do this now, I get, I'm going to expand my brackets first, because remember, we wanted to differentiate this because we want to find a maximum. Maximum means stationary points, which means that our derivative needs to be 0. If we're going to find the derivative, then we've got to have it in polynomial form. It's got to be all expanded first. So we'll have 50x minus x squared plus, I'll keep the 2 at the front for now, and I'll just deal with my brackets. So we'll get 100x minus 2x squared plus 250 minus 5x. All right. And now let's expand that bracket as well. This is a very long problem. Lots of places that you can make mistakes. So 50x minus x squared plus 200x minus 4x squared plus 500 minus 10x. And now let's combine our like terms together. So we've got 50x and minus 10x will give us 40x. We've got minus x squared and minus 4x squared, so that gives us minus 5x squared. I missed this 200x. Whoops. Easy. Plus 500. Cool. So that's my area function. So a dash the derivative of my area is going to be 240 minus x. And we're looking for when this is a maximum. If we're going to be at a maximum, then the derivative must be 0. So 240 is going to be equal to 10x. So x is to be 24. Now I've got x is 24, then we can find the value of y. We know that y is equal to 50 minus x. So that's the same as 50 minus 24, which is 26. But the question didn't want us to find x and y. The question wanted us to find the length and the width of the largest sink if the total area of the sinks is to be a maximum. So I found x and y if the area is to be a maximum, but this isn't the length and width. So my length is 2x plus 5, which is 2 times 24 plus 5, which is 53 centimeters. And my width is 2y, which is 2 times 26, which is 52 centimeters. If we were doing this problem, then we'd probably have 1 mark for getting to this stage here, 1 mark for getting to this stage here for finding the derivative, 1 mark for x and y, and then 1 mark each for our final results, depending on the quality of the answer. Okay, so last questions. First one, we've got h of x is equal to 2 minus 1 on x. We've got the graph there, nice and handy for us. We need to find in part A the instantaneous rate of change of h at the point where x equals 1. If you see this word rate of change, that means you need to go to the gradient. If you see the word instantaneous, that means you need to go to the derivative. So if we're finding the instantaneous rate of change where x equals 1, that means we're finding the value of the derivative when x equals 1. So first we need to find the derivative, but since I have, we'll just write this as h of x. Since I have x on the bottom, I need to move x to the top first. So this will be the same as 2 minus x to the power of minus 1. Now it's way easier for us to find the derivative, h dash of x, which is going to be the same as 2 plus x to the minus 2. And so this derivative is the same, sorry, no 2 there. It's just x to the power of minus 2. And then we'll have 1 on x squared. So h dash of 1 is going to be 1 over 1 squared, which is 1. Next part, so part B, is asking for the average rate of change. So rate of change still means gradient, but this time we want the average. Average rate of change is just what you've been doing in year 10, it's what you've been doing in year 9, it's what you've been doing in year 8. It's just the rise over run. So we can write it a bit more fancily, I guess you'd call it. So I'm going to call it M for our average gradient. Rise over run, well, I'm starting at h of 1. Sorry, I'm finishing at h of 1. I'm starting at h of 1 half. And I'm starting at 1. I'm finishing at 1 half in x. So h of 1 is 2 minus 1 is 1. And then h of 1 half, I'll just do that over to the side here. H of 1 half is equal to 2 minus 1 over 1 half. When we divide by a fraction, that's the same as doing the reciprocal of the fraction. That's 2 minus 2, which is 0. So it'll be 1 minus 0 over 1 divided by half is 1 half. So this will be 1 over 1 half, which just equals 2. So plenty plenty of fractions in this exam. If I was divvying up the marks for this, would probably have 1 mark for, probably 1 mark for filling this incorrectly. That would be 1 mark there for figuring out what your h of 1 half is, and then 1 mark for your final answer. Okay, I hope this has been helpful. If you do have any questions, feel free to email me or ask your teacher about this. Good luck with your exam revision.